We have invited speaker Perdikaris from Department of Mechanical Engineering and Applied Mechanics at the University of Pennsylvania. So his research topics involves physics-informed machine learning, uncertainty quantification in deep learning, engineering optimal design, and data-driven non-invasive medical diagnostics. So thank you, Paris, giving us a talk titled Understanding and Mitigating Gradient Flow Pathology in Physics-Informed Neural Networks.
Right, so yeah, thank you very much, Eric and Harry, for the invitation and the introduction. And good afternoon for everybody that is tuning in. So just to check, everybody can see my screen and hear me?
Yeah, perfect, yeah, no problem.
Yes, yes.
All right, great. So today I will be sharing some recent work that is joined with one of my students, Sifan Wang at UPenn, and supported by DOE, DARPA, and the Air Force. On understanding and mitigating some certain pathologies of physics-informed neural networks, which we already saw some lectures in the morning around this concept, and then there will be some lectures also tomorrow. But today I'd like to motivate this topic, start with the bigger picture, which is how can one bake in physics or physical knowledge into deep learning, essentially. And that is aligned with one DARPA project that is coming to an end. It's been running for the last year and a half or so on the physics of artificial intelligence. And essentially there were two schools of thought that emerged out of this project that had to do precisely with how one can embed physics into neural network architectures. So the first school of thought is aligned with the notion that physics can be implicitly baked through architecture design. So by coming up with specialized neural architectures that have very strong inductive biases and can implicitly bake in any known prior information about the physical system. For instance, we can construct neural networks that return predictions which are invariant to simple group symmetries, such as translations, of course, in the case of convolutional neural networks, or rotations or permutations, or some even slightly more complex symmetry groups. The advantage of this approach is that the physics is implicitly baked in, and we have, at the end of the day, one can come up with a highly regularized model that can efficiently learn from a relatively small amount of data and have good capacity to generalize and extrapolate. On the downside, oftentimes these specialized architectures require a radical design. Essentially, people cannot really rely on existing software tools, say like PyTorch or TensorFlow, but have to build those implementations from ground up. And those approaches come with significant computational complexity, and they're not as user-friendly as we would wish to this day. And one example is the recent work of Rishi Kondor on convariant compositional networks for learning on graphs and modeling many-body interactions in many-body systems. The second school of thought is essentially maybe the easy way out, in which one uses standard neural network architectures as a starting point. So for instance, standard fully connected networks, convolutional or recurrent networks, and then tries to bring in the physics explicitly this time by imposing constraints in the loss function of that neural network during training. And this is the main approach that I will focus today, and this is what defines this framework that we call physics-informed neural networks, in particular the context of baking in physical knowledge that comes from partial differential equations. All right, so let me give you an overview of physics-informed neural networks, just a few slides. Basically, this framework is used to seamlessly integrate any known physical knowledge in the form of partial differential equations with measurements. So the starting point is that we have some known physical law, and that is a general form, as you see in the slide, some function of x and u, the latent unknown solution and the derivatives of u and so forth, maybe potentially some unknown parameters lambda, and then subject to appropriate initial or boundary conditions such that the problem is well posed. So now, very similarly to what people have traditionally done in scientific computing, we will choose to represent the solution not with a polynomial basis expansion, but this time with a nonlinear representation, such as a neural network. And that would be a continuous and differentiable representation. Namely, for instance, the function u could be a function of space and time coordinates. So those two inputs, x and t, could be fed into a feed-forward neural architecture. Let it be, let's say for simplicity, a fully connected network. And then we can observe an output U, which could be either scalar valued or vector valued. And then since this representation is differentiable, we can apply any derivative operators. For instance, we can differentiate with respect to time or space, compute higher order derivatives and so forth. And that will allow us to compute the residual of the given equation. Using now this residual, we can formulate a loss function that has two goals. On one hand, it has a goal of fitting any available data that we may have observed, and those could be initial or boundary conditions, or in general, some other measurements that we may have collected for some of the variables of interest. And then the second goal is to minimize the residual of the PDE itself, and also the fit to any boundary or initial conditions. And that will define a loss function which we will use to optimize the parameters of our representation, namely theta, the weights and the biases of the neural network, typically using first order optimization in the form of stochastic gradient descent. So now this is not a new idea at all. So people in the early 90s have first thought of using deep neural networks to simulate, to solve forwards or inverse problems involving differential equations. But the main difference now is that we will rely on sophisticated software implementations which allow us to compute all the necessary derivatives using automatic differentiation. So people in the 90s had to sit down and derive all those forward passes and backward passes manually. Now we will rely on automatic differentiation to simplify our life. Not only that, that allows us to tackle some more complex problems which manual derivations become tedious or even infeasible. And then I'm providing a list of references just to highlight what has been done in the 90s versus what has been done recently. All right, so a few more details just to pose the problem in the context of PINNs. So that's the abbreviation for physics and for neural networks. Basically, we will consider PDEs of the general form shown in the top of the slide. So subscript denote differentiation. So UT is the time derivative of the latent solution U, and X is some nonlinear, general, potentially nonlinear differential operator. And then we have appropriate boundary and initial conditions. So we will proceed by approximating the unknown solution using a deep neural network. Let's note denoted by F with subscript theta, with parameters theta. And as soon as we do that, we can actually compute the residual of that equation, namely just plug in the neural network representation into the equation and compute the residual using automatic differentiation, and use that to construct a composite loss function that has several terms. One term wants to fit available measurements, another term to minimize the PD residual, and also fit the initial and boundary conditions. And that loss function will be minimized using gradient descent, where all the gradients are computed using automatic differentiation. So let me just walk you through a simple example, because the implementation of such an approach is really, really simple, leveraging software like TensorFlow. So here's a viscous-Burgers equation in one dimension, so the prototype nonlinear conservation law, where I'm choosing a very small value for the viscosity, subject to some initial and boundary conditions. And pretty much this is the code, the pseudocode that one needs to write to implement a solver for this equation using deep neural nets in TensorFlow. So basically you just need to define a neural network that pushes inputs and produces an output evaluation of the solution U. And then we can compute the residual, which I'm denoting as this quantity F, which is the left-hand side of the equation, simply by using a command called tf.gradients to compute the appropriate gradients. All right, so now in this case, one may have access to some observations, and these observations stem from the knowledge of the initial and boundary conditions. So you see now some data points denoted by those black X's. At t equals 0, we have a bunch of measurements across the domain, the spatial coordinate X. These are the initial conditions, and then at all the other times, we have some scattered measurements of the boundary data. So now these data will be used to minimize a data fit term. And then there will be a second term, which is the penalization of the residual of the equation, which is evaluated at a set of fictitious collocation points that we have the freedom to place anywhere we want in the domain. Not only that, since we're using stochastic gradient descent to solve the optimization problem, we can practically generate a mini batch of collocation points at every iteration of our gradient-based optimizer So in principle, we can have a really, really large number of collocation points spanning the entire computational domain. So now formulating a loss function like this, we can train the neural network and then assess the quality and the accuracy of the predictions. And then now what you see here is just a simple plot showing at different time instances that the predicted solution agrees very well with the exact solution for this problem that is available from the Kohlhoff transform. So now this is a deceivingly simple problem because many of you know if you want to resolve and compute a solution with reasonable accuracy for this 1D Burger's equation using classical numerical methods, you need to be very, very careful on how you discretize the problem, especially around the location of the sharp gradients around x equals 0. While here, you know, that doesn't seem to play a role. So the neural network has the capacity to approximate the solution, and then fairly easily we can get some, you know, fairly accurate solution and also, you know, in 60 seconds on a single GPU card, including the training time. All right, so this framework has been extended over the last 2 or 3 years, and there's been a lot of follow-up works. Perhaps most notably, here's a recent work that appeared in Science, coming from Maziar Raisi, Alireza Yazdani, and George Kaniadakis, where essentially they extend these PINN models to an inverse problem setting in fluid mechanics. So basically in this case, it's a more impressive application in which they consider the availability of concentration data of the, you know, some passive scalar that gets advected in a flow through an aneurysm. So, and then by considering some measurements of this concentration variable across 2 of those sliced planes inside the aneurysm, they can directly infer the underlying velocity field and the pressure. So these hidden variables can be extracted from the concentration measurements alongside with the knowledge that the system should be governed by the incompressible Navier-Stokes equations. So I'm not going to spend too much time discussing these results. I know that Maziar Raisi is giving a talk tomorrow morning, and he'll give us a much better overview of these examples. I just want to highlight, you know, just some other works that have appeared that extend this framework of physics-informed neural networks to both extremes, namely systems discovery from ODEs or PDEs, or solving PDEs, either in high dimensions, stochastic PDEs, constructing surrogate models. Earlier, we saw Marta talking about non-local and fractional PDEs. And then Lou will also discuss tomorrow, I think, about some integrated software that came out of the group at Brown. But the focus of today's talk is not so much on the success stories of PINNs, but I'll try to revisit the formulation and highlight some of the difficulties and some of the pathologies that may arise during training of such models. So let me first start by saying that the loss functions we formulate, again, they have several different terms, some terms trying to fit data and some other terms are trying to impose the physics. And physics acts as a prior, essentially, in this setting. So you can see that equation at the top as a maximum a posteriori estimate of a Bayesian model where the residual of the PDE acts as a prior for our formulation. So recent results showcase a lot of promise, but there's a lot of tricky cases, and failure looms even for the simplest problems. And here's just an example. So just consider a simple elliptic equation in 2 dimensions, the Helmholtz problem, subject to boundary conditions. So in the left-hand side, you see the exact solution for this problem, which is fabricated. And then on the right-hand side, you see a prediction of a 4-layer deep PINN model, which may look reasonable, but once you compute the relative error in the L2 norm between the exact and the prediction, you get an error of about 20%. No matter how much you try to fine-tune things and change the architecture, it is hard to get a more accurate solution than this. So now the question is, why does that happen? And can we gain some understanding of what's going on? But before we do so, I would like to stress out that introducing physics in this form essentially poses a functional constraint. It constrains the functional outputs of our neural network, and is not simply the conventional regularizer that we're used to in deep learning, which is just some L2 penalty or L1 penalty on the neural network weights. So essentially, it's an unconventional regularizer that in many times requires us to revisit standard practices, and it's very sensitive on the behavior of the model becomes very sensitive on the choice of the loss function, the initialization of the network, how the problem is normalized, the optimization algorithm, and the neural architecture itself. So the focus of today's talk will be around the last two bullets, and we'll try to analyze some pathologies that often arise in PINN models and try to mitigate them by proposing some new, novel adaptive learning rate strategies and improved neural network architectures. All right, so let's get started. All right, so here's the main hypothesis behind this work. And let me illustrate it using, again, this very simple 2D Helmholtz equation. In this case, the loss function has two terms. Essentially, it has a term that's trying to minimize the residual of the Helmholtz equation inside the domain, plus another term that is trying to penalize Dirichlet data on the domain boundaries. And now our hypothesis is that different terms in this loss function may have different nature. In fact, they have different nature, they have different units, different magnitudes, and that may lead to imbalanced gradients during back propagation. And then just to confirm this hypothesis, and what you see in this slide is during the training of the neural network that I presented in the last slide, so a simple feed-forward network with 4 hidden layers. So during training of this network, we can actually pause the training and compute the histograms, compute the distribution of gradients, of back-propagated gradients at each layer of this neural network, corresponding to each one of the terms in our loss function. So we have the gradients, the back-propagated gradients that are contributed by the boundary data loss, and also that is colored in blue, and the back-propagated gradients that originate from the residual loss. And then you see here an imbalance. Basically, the gradients that originate from the boundary loss, they all collapse around 0. So essentially, most of the gradient values in layer 2 or 3 and 4 are practically 0. So that means that the parameters during backpropagation and during gradient descent, the parameters of the neural network cannot be tweaked, cannot really see the boundary loss, and they're not changing with the goal of fitting the boundary data. So we end up having a model that may be able to minimize the residual, but it cannot really fit the boundary data. And as you all well know, if we don't fit the boundary data for the simple elliptic problem, there is no hope to get the correct solution. All right, so this is just a manifestation of the pathology, the imbalance in the back-propagated gradient. So now the next step is, can we do some analysis and try to pin down the reasons where does this imbalance is generated? So now moving on to the next slide, I will simplify the problem a little bit to make it amenable to analysis. So let's go back to a simpler case, and that is a Poisson equation in 1 dimension in a domain, a simple domain from 0 to 1, subject to Dirichlet boundary conditions. And now let us consider solutions, exact solutions for this problem that take this form of a sinusoidal wave with the parameter capital C modulating the frequency of the solution. So now essentially we want to see how a neural network approximation would behave for different values of C. So to do so, again, we can form a PINN model, we can formulate a composite loss function that minimizes the residual and the fit for the boundary data. And under some mild assumptions on how we represent this neural network function f of theta, one can actually derive bounds for the norm of the backpropagated gradients in the L infinity norm. And what you see there is that the norm of the residual scales as the 4th power of this parameter C. So for large values of C, the norm of the gradients of the residual loss will be much, much larger of the norm of the gradients of the boundary loss, therefore causing this imbalance that we observe numerically. And in fact, that is the case. For simple numerical studies, we can actually change the values of the C parameter and observe exactly this behavior. For C equals 1, this plot is not very informative because I try to keep the scales fixed from -2 to 2. But for C equals 1, the magnitudes of the gradients and the distribution of the gradients between the boundary term and the residual term are fairly balanced. But as we increase the value of the C parameter, the imbalance of the gradients becomes more and more pronounced. So again, this imbalance of the gradients is just a manifestation of the main cause. And the goal of our recent work is to to investigate what is the root cause of this problem. And to our understanding to this day, this comes from stiffness in the dynamics of the gradient descent, of the gradient flow. So basically, if you take the continuous limit of gradient descent, you obtain the gradient flow ODE system. And essentially, what happens during gradient descent is that we discretize this ODE using a forward Euler discretization. We start from some initial guess for our parameters theta. So again, theta is the vector of parameters of the neural network, all the weights and the biases. And then we integrate this ODE to reach an equilibrium point, which will correspond to some local minimum of the system that will give us the trained neural network. And now I'm writing the right-hand side of this equation in general form. As you see, I have a residual term corresponds to the PD residual, and then maybe we have a collection of different terms that correspond to data fit terms. So either measurements inside the domain or initial or boundary data. So now our main hypothesis is that stiffness exists in the gradient flow dynamics of physics-informed neural networks. And by stiffness, I mean that the largest eigenvalue of the Hessian of this neural network will attain very large values. Essentially, this is how stiffness is characterized if we look into the linearized, if we perform a linear stability analysis for this ODE system. And then consequently, the stiffness leads to imbalanced gradients during model training, and that hamper the performance of gradient descent algorithms. So this is the main hypothesis. So here's a simple example, again, going back to the Helmholtz equation, in which again, I'm fabricating an exact solution that has a form sine A1 pi x times sine A2 pi x, where now those two parameters A1 and A2 can be changed to modulate the complexity of the solution. And what you see in the plot of the right is is recording the largest eigenvalue of the Hessian of a neural network approximation for this problem for different values of A1 and A2. So if we keep A1 equal to A2, we obtain a relatively simple solution, and that's sort of the non-stiff regime. Whereas when we introduce more oscillations in our solution in the X direction, or sorry, in the Y direction, by increasing the value for A2, we obtain a much stiffer gradient descent problem. And basically, the pathologies that we have observed in practice are closely related to the choice of gradient descent as a training algorithm. Basically, we're trying to use a forward Euler discretization to integrate a very stiff ODE. And of course, as you all know, that has severe restrictions on the step size that one can use. So to make things work and to have a robust PINN model, one will have to reduce the learning rate, eta, of the gradient descent algorithm to very, very small values that renders the use of PINNs pretty much not practical for realistic problems. Because even for this simple Helmholtz equation, training could take hours to days if we set a learning rate of 10 to the -6 or 10 to the -7. All right, so a little bit more analysis on the stiffness and some interesting results. So let's stay to the setting and use the Helmholtz equation into D as our prototype problem. And now we can write down the gradient descent update rule, and we can decompose it in terms of the two terms in the loss function. So we have the residual L of R and then the boundary term L of UB. And then by applying second order Taylor expansions to the loss function and performing an eigen decomposition of the Hessian, one can show, one can show that the two consecutive values of the loss, so basically we have the difference, this is the loss function evaluated at iteration n+1 minus the loss function at iteration n, may not decrease. So this is the take home message here. So if the eigenvalues of the Hessian, if the problem becomes stiff, then there is no guarantees that taking a gradient descent step is guaranteed to decrease our loss function at every iteration. And basically, for this simple example, the two plots in the bottom show exactly that. For the stiff case, where A1 is equal to 1 and A4 is equal to 4, the Hessian matrix of the neural network attains very large eigenvalues. And then even if one uses full batch gradient descent to optimize the objective function, can get trapped in limit cycles and does not observe a monotonic decrease of the loss function. So you see a lot of oscillations in the loss function of the residual term, which is the one that introduces the stiffness to this problem. Okay, so now, essentially, this is some analytical confirmation and also some numerical evidence that stiffness exists in the gradient flow problem of physics-informed neural networks, and also an indication that just using blindly vanilla gradient descent or its variants like Adam may be a poor choice for training these constrained neural networks. So now the question is, what can we do, right? I mean, we have a stiff problem and we want to integrate it to equilibrium to get a good set of parameters for our neural network. Well, looking back in the numerical analysis literature, either we can use implicit methods that have much better stability properties, or multi-rate methods, essentially try to come up with strategies to adjust the step size of our integrator to come up with a more stable and robust solution. So implicit methods are very intimately related to proximal gradient algorithms in the optimization literature, and that's something that we are working on these days. But this work and this presentation that I'm giving today will focus on explicit methods with variable step sizes, so essentially resembling multi-rate integrators for ODEs. So let's stick again with this simple 2D benchmark of the Helmholtz equation. And basically now what we'll try to do is introduce some weights, multiply the different terms in our loss function with different weight parameters, as you see in the top right of the slide, lambda 1 and lambda 2. So now it turns out that there exists some magic combination of lambda 1 and lambda 2 for which we can train this neural network and get a very accurate or a reasonably accurate prediction of the solution that no longer has large errors at the domain boundaries. So remember, before the error was about 20% in the relative L2 norm, and now it's about 0.5%. Not only that, if we plot the histograms of the back-propagated gradients at some point during our model training, we see a much better balance between the gradients originating from the boundary loss and the gradients originating from the residual loss. And essentially these parameters, lambda 1 and lambda 2, these weights, you could think of them as adjusting the learning rate, as scaling the learning rate of our problem. So now the main question is, obviously, how do we choose those weights or learning rates? And to this end, there are three different approaches one could employ. So one, we can perform essentially what people call meta-learning or hyperparameter tuning. So essentially just throw a lot of computational resources to the problem and perform an exhaustive hyperparameter search that will come up with the right combination of weights. The second one is...
Sorry, just a quick question here. Mm-hmm. Let's say you calculate you do backpropagation, you calculate the gradient for each term, the UR, U0, UB. And then based, for example, on the magnitude of the gradient, you adjust the lambda so that everybody's magnitude 1 or something like that. Is this sufficient or not?
Yeah, essentially this is where I'm heading to.
Sorry.
That would be our strategy to adjust the lambdas in an automatic fashion.
Okay. Yeah. Sorry. Okay. Thanks. Yeah. Thank you.
Right. So yeah. So basically, one approach is to perform hyperparameter search. The other one is just to tweak those parameters manually and hope for the best. And the third one is try to come up with a way of automatically tuning those parameters. And that's exactly what we will do by utilizing the gradient statistics during training. And this idea actually is very, very similar to the most widely used optimization algorithm in deep learning, namely Adam, which essentially does exactly the same thing. So at every step of the optimization, Adam is updating, is trying to come up with some online estimates for the first and the second moment of the gradients, and is using this information to adjust the learning rate accordingly. So now the basic idea of these adaptive learning rate optimizers is to utilize gradient statistics during training to adaptively adjust the learning rate. And this is exactly what we will do in our case as well, with the goal of balancing the interplay of the different terms in the loss function. So basically, this is the algorithm that we have recently proposed. So the starting point is some loss function that has a composite form with multiple interacting terms. And now we will introduce these scaling coefficients lambda I, which will be initialized to 1 at the beginning of the training, and will be updated as the gradient descent algorithm evolves using equation 40, basically, equation 40 and 41. So equation 40 obtains an estimate for the lambda i's that is trying to balance the magnitude of the gradients originating from the residual term and the gradients originating from each one of the I terms in the sum. We have M terms that could be data fit terms, and so consequently we have M weights that we need to tune. And then in equation 41, we will just smooth out, we will just take a running average of those lambda hat i's, mainly for smoothing purposes, because we're using stochastic gradient descent, and the estimate obtained from equation 40 could be very noisy. So now we can perform a running average to obtain a smoother parameter value. And then finally, we will perform traditional gradient descent updates using the update rule in equation 42, in which you see now that those parameters lambda I will multiply the learning rate eta, and accordingly tweak the learning rate with the goal of balancing again the gradients of the residual and the data fit terms in as seen in equation 40. All right, so this is the main modification. Basically now during model training, we just have to keep track. It's a matter of bookkeeping, of computing the gradient statistics and utilizing them for computing those adaptive weights. And this does not have to be performed in every single iteration of gradient descent. So those updates, so those lambda i's can be updated every 10 iterations or every 100. Yeah, so it doesn't have to be done at every iteration to save on some computational cost from computing those gradient statistics or storing them. Okay, so just a recap before I show you some results. Essentially, we're operating in the regime in which we want to impose physics as a soft penalty constraint in the loss function of neural networks, and that introduces an unconventional regularizer. And then we've done a lot of work and experimenting with different kinds of loss functions using either square residuals or variational energy type loss functions. We've tried different things with network initialization or normalizing the solution in different ways. And all of those bullets contribute to what I refer to as stiffness in the gradient flow problem. So one can end up with a stiffer or less stiff problem by revisiting any of those bullets and making appropriate choices. So one of the directions that we actually investigated was whether modifications in the neural network architecture could result into significant improvements in terms of reducing the stiffness and obtaining more robust solution. And one simple idea that seemed to work very well in practice, and this is just all empirical evidence that we have in this direction, is to slightly modify fully connected architectures by the introduction of some additional weight and biases parameters, namely W1 and W2, and modify the forward pass of a neural network using the equations that you see in the top of the slide. So trying to break this down into some simpler pieces. Now, if you neglect, if we focus on the sketch in the middle of the slide, so the mapping from X to F theta through the capital H hidden layers, essentially that is a fully connected neural network. So now we have two additional mappings that take the inputs and map them into some latent spaces, U and V. And now the update rule for the hidden layers, H1 to HL, is obtained using point-wise multiplication with those hidden latent representations that are contained in capital U and capital V. And this is a very simple architecture that sort of resembles some features observed in LSTM architectures. But basically, the main key point here is that this architecture can account for multiplicative interactions between the inputs, similar to what the deep learning community refers to as attention mechanisms. And then the second part is that residual connections seem to improve the resilience against vanishing gradients and also provide some robustness with respect to different neural network initializations. And again, this is all empirical evidence, but this is something that we found in all numerical examples that we conducted. This architecture was performing universally better than standard fully connected models. So using, again, the 2D Helmholtz example that I presented earlier as a benchmark, here I have collected 4 different approaches or 4 different models that we have tested to assess, the accuracy of our prediction. So M1 will denote the baseline PINN model that was put forth in our paper with Mazia Raisi and Jos Karniadakis. Model M2 will refer to the same PINN model, the same architecture, but now using the proposed learning rate annealing algorithm that I presented a few slides ago. Model M3 will be a standard PINN model, will be a PINN model with the proposed neural architecture that I just showed you, but using plain gradient descent, so no adaptation of the learning rate. And then model 4 is putting everything together, namely using the proposed architecture and the learning rate annealing schedule together. And what you see here, this is just a relative error in the L2 norm against the exact solution that is averaged over 10 independent trials for different neural network architectures. You see that model M4 universally provides the best accuracy that improves the baseline model for about 1 or 2 orders of magnitude consistently across different architectures. So that was the main benchmark for which we did our exhaustive systematic studies. Then we tried different examples also to make sure that things remain consistent. So here's another problem that traditional PINN models have a lot of trouble with, and this is the wave equation. So that involves the second derivative with respect to time and second derivative with respect to space, subject to initial and boundary conditions. And if you train a PINN model for this problem to obtain the solution, things become really, really tricky unless an extremely small learning rate is chosen. In fact, to confirm my intuition, I tried to train a simple PINN model for this problem using a learning rate of 10 to the negative 7. Training took about 4 weeks to complete, and the results were reasonable. But if you try to repeat that with a learning rate that is, the practical order of magnitude, let's say 10 to the negative 3 or 10 to the negative 4, you will obtain a plot like you see in the top row of the slide. So the exact solution is on the left, and the middle one is the predicted solution of a standard physics-informed neural network with 5 hidden layers. And the relative L2 error in this case around 76%. While in the bottom row of this slide, you see the same exact prediction for exactly the same architecture, but now using the improved learning, the proposed learning rate annealing schedule and the improved architecture that I presented a few slides ago. And the error can be reduced about 0.6%, so a few orders of magnitude in improvement. And then we have investigated different examples. So that's a slightly more complicated example in wave propagation, the nonlinear Klein-Gordon equation. Again, we see consistent improvements. In this case, PINNs, the standard PINNs approach could also perform reasonably well, but still the error was around 7%, whereas our prediction has an error of about 0.1%. And then finally, we also did an exhaustive study for fluids, a canonical fluids problem, the flow in a lid-driven cavity, in which case all models were able to give some approximation to the solution, but consistently the adaptive learning rate annealing model and the improved neural network architecture gives the best results, again, resulting into an order of magnitude in improvement in predictive accuracy. So I think I went a little bit fast. I just have my summary slide, but that leaves us with a lot of time for discussion, which I'm looking forward to. So let me just summarize by saying again that function space constraints introduce unconventional regularizers that often requires us to revisit standard deep learning practices. And I would say that it's ill-advised from my experience to employ deep learning models as a black box and try to throw them into these physics constrained type of problems. So using gradient descent as a black box or initializing a neural network using standard practices may not be the right thing to do. Those constraints alter the loss landscape of our neural network. They introduce competition between different terms in our loss function that may lead to stiffness and imbalanced gradients. Adaptive learning rate schedules can help to mitigate this interplay and to balance the interplay of the different terms. Different neural network architectures, that's a big question. So we've been using fully connected networks, which is probably the most naive thing one can do in the sense that the inductive biases introduced by our model are extremely weak. So there's a big open question there, what would be the right neural network architecture to use for this type of problems? And then using the proposed developments, we observe a consistent improvement in the predictive accuracy of PINNs, consistently by a factor of 50 to 100 across different problems. And what I would like to stress out, my work has been focused on PINNs recently, but I think that these techniques also generalize and are very relevant to other tasks in machine learning that involve the interplay of multiple objective functions. And that is essentially the setting seen in multitask learning cases. And then despite some progress, we're still at the very early stages of really understanding the underlying mechanics of this model and what really happens when we're trying to train them. So with that, I would like to conclude and open the floor to discussion. So thank you very much again.
Okay, thank you for the great talk. So we have about 20 minutes for the discussion and questions. So if you have any questions, just leave it, just interrupt me.
Hi, Paris, this is Panos.
Hi, Panos.
So very nice talk, thank you. When you say you average the gradient with respect to the parameters theta, what average are you talking about?
Okay, let me go to the main algorithm. You mean here, right?
Yes, in expression 40. This, yeah. You say that the bar quantity denotes the mean with respect to parameters theta. What do you mean with respect to parameters theta?
Okay, sorry. This is, it's not, the mean is not taken with respect to parameters theta. This is just the average of the gradient values.
When you say average of the gradient values but where does the variation come from? So
at every hidden layer, we have a collection of neurons, right? So,
I see. Okay.
So the average over all activations for the back-propagated gradients.
Does this, okay, so in order to do this, do you need all the layers to have the same width?
Not necessarily. In fact, you can do this adaptation per layer, which is something that we haven't done. But for now, we just concatenate all gradient values and then average.
Okay. So, okay. All right. Now, just a quick, I don't know, comment question. It's very interesting that in traditional numerical analysis in PDEs, right? The most difficult thing is how to enforce the correct boundary conditions. So, and I see here an analog of this situation that somehow it is easier to back-propagate the form of the equation, but when it comes to actually back-propagating the information from the boundary conditions, it's much more difficult, right?
Yep.
So you have to use the parameter lambda to amplify the transfer of information from the boundary conditions to the actual parameters.
Yeah, that is correct. And I didn't show it in my slide, but from the numerical studies, we observed that those lambdas typically converge to some plateau after 5 to 10,000 gradient descent iterations, and usually take values of order 10 to the power of 2 or 10 to the power of 3.
Yeah, so which means that they really need a lot of help in order to. Right. Okay. Thank you.
Yes.
Excuse me, this is.
Chat, So sorry, there was a question in the chat from William Tucker. So if he wants to ask now, maybe he wants me to read the question. So the question was, are there any Python modules we can play with yet? William
Um,
Tucker.
Please send me an email. So the paper is under review. We have already some tutorials and we have shared them with different groups. I know that George Karniadakis, they really performed an exhaustive study trying to reproduce our results, and we have helped them with providing tutorials. So if you guys need some sample code, just shoot me an email and I'm happy to share. And obviously all the code and data that are related to the paper will be online as soon as we get the reviews back.
Thank you.
Hello, this is Matteo from NASA Ames. I have a question, like, that's a great presentation, by the way, but I have a question about, so what's your understanding of the, how accurate this, embedding of the physics is when you have a non-perfect knowledge of the PD? Because it seems to me, I don't know if I'm wrong, but it seems to me that when you compute the residual on the PDE, you are actually writing the correct PDE in your loss function. So let's say that I don't have a perfect knowledge, or maybe I have like some parameters of the PDE are unknown or are time varying. So what's your take on how good it's going to perform?
So I think on this front, you're going to hear a lot more tomorrow when Mazia Raisi and also Chris Rakauskas from MIT present their work, which is essentially focused on this, inverse problems and cases where your PDE may be imperfect and you're missing closure terms or constitutive equations and so forth. My only comment to this is that these frameworks are very sort of easy to adapt and implement. So it's easy to, we have now the tools in terms of software to prototype and test things out using, automatic differentiation and this type of constraints. So the framework is applicable to the setting you described, and I'm sure that tomorrow we will see, really nice applications in this direction.
Okay, thanks.
Mm-hmm.
So maybe I have a question. Can you come back to the your slide with your new architecture with UV and the multiplication?
Yeah.
It was kind of more of a common question / comment. So one thing is I can see that because you're sort of connecting, all layers to this U and V, that, you're mentioning your resilience against vanishing gradients. So I can see how this may happen because of this connection between, layers at different depths and so on, all connected to U and V. But I was wondering if you had tried something different, but perhaps might work as well. So in ResNet, you typically have connections between, every other layer or maybe a certain stride. But you can imagine a type of ResNet where, you make connections between, layers with stride, 2, 4, 8, in this fashion, so that you sort of have a global connection in some sense between layers. I wonder if you've looked into that or...
Yeah, so we did experiment a little bit with resonance. By no means that was an exhaustive, architecture search. And we do indeed observe that there is an effect of the architecture in relation to the stiffness aspect that I just described. The tweaks in the architecture could lead to a stiffer or less stiff problem. Again, it's not sufficient to entirely solve all the pathologies, but it may allow you to train the neural network with a slightly larger learning rate or slightly faster.
But my question was more about having a ResNet with different strides at the same time.
So no, that's something that we haven't,
Okay. I was just curious.
Hi, Eric. Well, I actually wrote a paper with someone else that had to do with that. So, which we call them shortcuts, so instead of using, which what you're talking about ResNets where you can, go not just every other layer, but maybe even connect the first and the last layer. So we showed there using simple examples from the standard literature for computer vision that in fact it helps a lot. It helps a lot and accelerates a lot the training process. You will not necessarily get a better accuracy in the end, but actually you will get to the good result faster.
That's right. That's right. Okay.
So, and the reason why this is done, you can actually study it by using the mutual information, and you show that basically what happens is that through this mutual information, you can show that even when you have a network with millions of weights, the effective dimension that you're looking for to optimize is much, much smaller because of these shortcuts. So they do help, and not just, like I said, in strides of more than one.
Mm-hmm.
Yeah. That's right. Okay. No,
but not for these problems, right? It was just for computer vision problems.
I have a question for Paris.
Yep.
This is Nat from Sandia. For this architecture, have you looked at what, right, so this is implicitly defining a basis. Have you looked at what those basis functions look like?
You meaning at the whatever sits at the last layer of the network?
Yeah, exactly. Right. You're taking a linear, you hit it with a linear layer at the end, right?
Yeah, that's right. Yeah. No, we haven't really looked into that. And that's a great point to see whether there's any insight or information that we can extract from that.
Yeah, I'm curious whether, you know, the approximation space that you're constructing, if it works differently or if it just trains faster, like more efficiently, but it's approximating in the same way as a normal feed.
Right. No, that's a very good point to compare the spaces of this architecture, say, you know, with using the U and the V's versus without, and see. Yeah, it's a good point.
Thanks.
Okay. So I have one question about your slide regarding the proximal method. So proximal optimization method. So do you have any kind of sharing with us about the proximal operator and then their optimization algorithm to this kind of problem?
So basically, proximal gradient descent is equivalent to, one can show that it's an equivalent to a backward Euler discretization of the gradient flow. And backward Euler is a method that is unconditionally stable regardless of the choice of the learning rate, right? One can improve the accuracy and reduce the truncation error by reducing the learning rate, but the method should be stable. So in these cases, I would not expect, if one was to employ a proximal gradient algorithm, hopefully you won't see this cyclic behavior and oscillations in the loss function as you see in this bottom right plot. We have some preliminary results with proximal gradient descent for PINNs, which indeed confirm some of our intuition on the stability, on the enhanced stability. But then that comes with an additional computational cost, because in order to implement an implicit optimizer, one either has to invert the Hessian or perform sub-iterations within every gradient descent step, perform sub-iterations to compute the proximal operator. And that is still a non-convex problem. So we're still trying to understand what is the effect of converging to a bad local minimum and how it affects the entire result. So this is still work in progress.
Okay, thank you.
Kind of somewhat related to that, there's also these methods, you have various second order methods like KFAC, for example. Might be interesting to see, how this improves convergence with these physics informed networks.
Absolutely, yeah. Moving towards the second order methods, it's really interesting. But of course, you have to come up with some approximations or factorizations of the Hessian that are computable.
Yeah, this is what KFAC is doing.
Yep.
They have, Okay, great.
So no more questions from audience? Okay, so we can wrap up, and so thank you again for the great talk, Paris.
Thank you very much.